some fundamental concepts are the topic of our discussion today. Main topics that I will be covering is fluids, fluid as a continuum, density, and specific weight. Let's talk a little bit about fluids. We started defining fluid from last lecture, but let's take another look at fluid. A fluid is a substance that may flow. The main difference between fluids and solids is that if we have a solid at an at-rest condition, meaning that in equilibrium condition, when we apply a force to it, it may or may not move. However, fluids don't behave that way. So if you have a fluid at rest and no shear forces can exist in it, which is different from solid. So it's very important to realize the difference between the fluid and solids. I mentioned the shear stresses last time and the resistance of solids to shear forces, whereas fluids, they don't exhibit that kind of a behavior. So if a shear force is applied to a fluid, it will cause it to flow. Continuum concept is a very important concept that I need to go over here. Of course, every fluid consists of atoms and molecules, and that's very important if you want to do a complete analysis and to look at a fluid at the molecular level. However, for the sake of engineering, we would take a rather more holistic approach to the problem. So we're not going to look at every individual particle to see how they behave, although we have that in mind that the basic substance of a fluid is actually molecules and atoms, and if you want to have a complete picture of what's going on, we need to look at it at the molecular scale. However, for the sake of fluid mechanics, we use a rather macro scale approach. So we do not consider the separate molecules. Rather, we assume that fluid is a continuum, and we look at it as such. So we assume that matter is continuous, the distribution of the matter is continuous, and there will be no empty spaces in between. And so if you look at this figure down here, I look at I represent a fluid mass as an entire mass P. P is the pressure that do exist within the fluid or gas as well. And so we are looking at a holistic approach, assuming that the entire light blue area, the sky blue area that I represented here, that is the view, a macroscopic view of a fluid particle, rather than looking at each individual molecule. So one must keep that in mind when we are analyzing any kind of a fluid mechanics situation. A more mathematical approach to this is when we look at the definition of density at a point. If we look at one particular point C at a volume of a mass, a small, very small, infinitesimally small volume of mass of a substance, of a fluid, we can assume that point C is made up these small particles, and if you want to look at the density to see what the density of that particle would be. Of course, we need to assume some area to be able to calculate the density over that area, and that, of course, depends on the coordination of the coordinate of the point C on XYZ plane, three-dimensional plane, and the volume that is actually it contains. So this is another really approach to try to describe fluid as a continuum. We try to avoid looking at the molecular behavior of fluid particles. Rather, we try to develop formulas and come up with definitions in which we can apply the principles of fluid mechanics to solve our engineering problems. In the process, it is very important to define the density here. Density is the amount of mass per unit volume of a substance, as shown here. Rho is m divided by v. Rho is the Greek letter we use for density. It's pretty common. I've never seen any book that use any other symbol for density. You may find some books, but in any case, mass divided by the volume of the substance, or a volume of a substance that have a mass, a volume of substance having a mass m. So the unit of density are kilograms per cubic meter in the SI system and slugs per cubic foot in the US customary systems. So V here is the volume of the substance having a mass m, and as such we can apply this formula every time the mass and volume is given. We can easily find the density, or if the density of a material is given, the volume is given, we can find mass, or if the density and mass of a substance is given, we can easily find the volume. So this is one of the fundamental formulas that we use in fluid mechanics to solve some of our wonderful engineering problems. The second equally important definition is specific weight. Specific weight is the amount of weight per unit volume of a substance. We use the Greek letter gamma for specific weight. Again, that's a common letter, a common symbol that you can find for specific weight. In this formula, in this definition, V is the volume of a substance having the weight W. The units for specific weight are newtons per cubic meter in the SI system and pound per cubic foot or cubic feet in the US customary systems. That brings me to the end of slides for this topic. Thank you.